Long before coal powered our modern cities, it lit the hearts of ancient China, heated the bathhouses of imperial Rome, and provided energy that forged swords, fired pottery, and fueled the expansion of empires. And thousands of years later, coal would do it again, only bigger, as it fed the furnaces of the Industrial Revolution that propelled industry and society into the modern era. But this progress came with consequence. Today, coal is a warning of choking skies, collapsing ecosystems, a climate off balance. But for something that changed the course of human history and the environment, we rarely stop to ask, where did coal come from? To answer this, we need to go back, way back, to a time before dinosaurs, a world blanketed by lush vegetation, mist, and heat. A world alive with the scuttling of huge insects and the creaking of giant plants. Because it's from this world, one extraordinary chapter in Earth's history, that most of the coal we've ever burnt was born. This is the story of coal and the world that made it. Our story begins over 300 million years ago during a geological period called the Carboniferous, which means coal-bearing in Latin. This period presents a truly captivating image. Immense, swampy forests blanketed the land, dominated by towering tree-like plants and tangled swamplands. Above them, pigeon-sized insects like the flying Meganeura buzzed overhead, while the huge millipede-like Arthroplura up to 2.5 meters long scoured the forest floors. And let's not forget the cat-sized scorpion, Pulmonoscorpius kirktonensis. It was by all definitions an age of extremes. During the Carboniferous, Earth's continents were arranged rather differently. Around the equator sat a landmass called the Russia, also known as Euramerica, made up of what we now know as North America, parts of Europe, and Greenland. Gondwana in the south was larger and included present-day South America, Africa, Antarctica, India, and Australia. Over millions of years, these massive landmasses slowly moved towards one another. Eventually, they began to collide, a slow, grinding convergence that would reshape the planet and eventually become Earth's most famous supercontinent, Pangaea. The journey to Pangaea was catastrophic. During the late Carboniferous, immense tectonic forces buckled and bent the Earth's crust, forming vast mountain chains close to the equator. As the mountains rose, the land around them sagged, forming large low-lying basins. These became warm, wet, and fertile, filled with thick vegetation and humid swamps. The perfect place for coal to form. As the continents evolved, so did Earth's climate. Let's rewind back to the start of the Carboniferous to see how things changed. The Carboniferous began as a warm tropical world where global temperatures averaged 20 degrees Celsius, 5 degrees hotter than today. In fact, the temperature was so uniform there were no seasons, evident by the lack of growth rings in the plant fossil record. This may have been due to the large expansive ocean, the Panthalassic, that covered most of the globe, providing relative climate stability. But then something happened. Around 340 million years ago, Earth entered what scientists call the Paleozoic Ice Age, and average global temperatures plummeted to around 13 degrees Celsius, slightly cooler than today. Scientists suggest that this was caused by intense mountain building of Pangaea and increased weathering of silicate rocks, a natural process that removes large amounts of CO2 from the atmosphere. At the same time, the growing equatorial swamp forests were hungry for more CO2, consuming so much of it that global temperatures cooled even more. As temperatures continued to drop, large ice sheets and glaciers developed at the South Pole. They expanded and shrank in cycles, causing global sea levels to rise and fall, just like a bathtub filling and draining. With all of this going on, you may wonder what made the Carboniferous the perfect factory for coal formation. Coal is formed from the remains of carbon-rich plant matter that has been buried under layers of sediment and subjected to intense heat and pressure. And during the Carboniferous, there were a lot of plants, many unlike any we have today. Take the towering scaly club mosses, the Lepidodendron and Sigillaria, reaching 50 meters high, and the fern-like horsetails that cover the swamp floors. These alien forests were among the most productive ecosystems the world has ever seen. But the Carboniferous wasn't just about how much plant life grew, it's also about how little of it decayed. These prehistoric swamp forests were incredibly efficient at capturing and storing carbon. As they grew, they sucked up hundreds of billions of tons of carbon dioxide, storing the carbon in their trunks, leaves, and roots. And when the plants died, their carbon-rich remains littered the swamp floors. Instead of decaying, they just piled up, layer after layer of peat, in the oxygen-starved swamp waters. With little or no oxygen, conditions that scientists called anoxic, organisms that would normally eat and help decompose the plant remains, such as fungi, microbes, and bacteria, struggled to survive. In fact, for decades, researchers believed this was the primary reason for such a large buildup of Carboniferous coal, a lack of decomposers in general. See, most modern plants contain lignin, a tough woody compound that gives stems their rigidity and resists microbial breakdown. According to a theory called the lignin lag, Earth simply hadn't yet evolved the fungi and microbes capable of digesting it. As a result, the plant matter remained, slowly compressing into peat and later forming coal. However, recent discoveries suggest a different reason. First, it turns out that the dominant plants of these coal swamps, particularly the club mosses, contain relatively little lignin to begin with. Second, we now know that lignin-eating microbes already existed as far back as the Devonian period, well before the peak of the Carboniferous. So, if lignin lag wasn't the main culprit, how did the Carboniferous swamps bury so much carbon? The answer lies in the rare combination of climate, geography, and tectonics. Near the equator, where the coal swamps were, the climate was just right. It was hot and humid, enabling vast rainforests and swamplands to thrive and absorb massive amounts of carbon dioxide from the atmosphere. At the South Pole, icehouse conditions of the Paleozoic Ice Age also played a vital role. Expanding and shrinking ice sheets locked up and released vast amounts of seawater, causing global sea levels to dramatically rise and fall. When the sea levels fell, the swamps dried out, but when they rose again, waters rapidly flooded the swamps, burying and preserving the dead plant material under layers of marine limestone and shale. This process repeated for millions of years, building distinctive layers of alternating coal, limestone, and shale that geologists called cyclothems. But like the coal-powered factories of the Industrial Revolution, the great Carboniferous coal factories eventually shut down. You see, about 307 million years ago, the lush rainforests and coal swamps vanished. Scientists call this the Carboniferous rainforest collapse, and it was a pivotal moment that marked the end of Carboniferous coal production. The reason for the collapse is debated, but it seems to come down to three main culprits. Over millions of years, the rainforests and swamplands' insatiable appetite for carbon dioxide caused levels to plummet. With less CO2 in the atmosphere, global temperatures started to drop, fast. At the same time, the Paleozoic Ice Age, which pulsed between long cold and shorter warm spells, continued to lock large amounts of water into the southern ice sheets, making the climate more arid with less moisture to quench the mighty vegetation. And if that wasn't enough, Pangaea was finally taking shape, with the crunching continents turning those wetland basins into drier highlands. This arid and cooler climate had a devastating impact on ecosystems adapted to a hotter, wetter world. However, as the great rainforest retreated and the coal swamps dried up, new species of plant, better suited to the new and variable climate, seized the opportunity to flourish as the great Carboniferous coal machine came to a stuttering stop. The towering leucopsids, once kings of the Carboniferous swamps, were replaced by seed ferns and early conifers, and the infamous Glossopteris, a plant fossil that would go on to help prove Pangaea existed and that the Earth's plates have been in constant motion. But even though the Carboniferous coal factories had shut down, this didn't spell the end of coal formation completely. It continued to develop through the Permian and beyond, but never to the same extent as the Carboniferous. Today, the great forests and swamps of the Carboniferous are gone. For millions of years, they trapped and buried trillions of tons of carbon, re-engineered the atmosphere, creating a colder and drier world. Just over 300 million years later, the Carboniferous coals are changing Earth's climate again. But this time, the coal isn't cooling the climate, it's causing it to heat up, and fast. We've mined and burned hundreds of billions of tons of coal since the start of the Industrial Revolution. releasing triple the amount of planet-warming carbon dioxide back into the atmosphere faster than nature can handle it. We're fast-tracking the Carboniferous in reverse, millions of years of CO2 pulled from the air, released back in mere centuries. As our climate continues to warm, what will our fate be? Will our world cease to exist, like the once mighty Carboniferous rainforests? Or can we halt our march to disaster? To do so, we must consign coal to the geological history books. Thanks for watching Earth Explained. If you found the story of the great Carboniferous coal factories interesting, please hit the like and subscribe button, it means a lot to us. If you're curious for more, tap the bell to know when we release our next extraordinary story about the planet we call home. We may only be a tiny part of a remarkable tale that spans billions of years, but we're the only ones who can tell it. Stay curious.